Thanks, Reed, for the invitation. And thanks for the organizers for putting the conference together. I enjoyed and learned a lot from the lovely talks yesterday of Rui and Zhikan. So sorry for the title change here, but the subject of the talk is the Mabuchi energy of an algebraic manifold, motivated obviously by the existence of constant scalar curvature metrics on such manifolds. So here's the setup. Let's see, get rid of this. Trying to get rid of this. Okay, a little better. So let X be a polarized manifold, a complex manifold. So L here is a ample line bundle on X, and H is a Hermitian metric on L. And we just say the curvature form is this. This is what my Kähler form is going to be. And recall that the space of Kähler metrics, beautiful H, are just all smooth functions on these omega pluri-subharmonic functions on X. So omega phi is omega plus dd bar phi, and this is supposed to be positive. So roughly speaking, phi has positive Hessian. And important player in my talk, and indeed in a lot of Kähler geometry, is the Mabuchi K-energy map, which is a functional from beautiful H to the reals. And this is its definition, where phi t is a C1 path in H, starting at 0 and ending at phi. It could be, for example, piecewise a C1. And the first thing Mabuchi showed when he introduced this action is that this is well-defined, so it's independent of the path. And the point, as you can see from looking at the expression for the Mabuchi energy, is that a Kähler potential in beautiful H is a critical point for the energy, if and only if the scalar curvature is constant. For example, if L is negative kx and omega is representative of the first Chern class of X, then the scalar curvature is constant. The constant here is mu. This is just depends on the class of omega and not on the metric. If and only if the metric is Kähler-Einstein. So constant scalar curvature in the anti-canonically and also canonically polarized case is just equivalent to being an Einstein metric. So important point about the Mabuchi energy in the presence of a metric of constant scalar curvature, or an Einstein metric in particular. I'll say it this way, proved by many people, Bondo and Mabuchi in probably 86, then Simon Donaldson in early 2000. Donaldson considered an arbitrary polarized manifold, not necessarily a Fano manifold, but he assumed the automorphism group was finite. And then Chi Li was able to remove the assumption of finite automorphisms. And what they showed is that if X admits a constant scalar curvature metric in the class of omega, then the Mabuchi energy is uniformly bounded from below on beautiful H. So this is important for my talk. And so that brings up the first question. And that's this one. So I just put it to you. How to detect or characterize when the Mabuchi energy is bounded from below on beautiful H. So you can ask this question, even if omega is not a Hodge class. It makes sense to ask this question on any, say, compact Kähler manifold. It's just getting an answer on any compact Kähler manifold, I think, is perhaps very difficult. And here's another way to put the question, a blunt way to put the question. And you can keep this in mind throughout my talk. And that is, what's the infimum? Let's suppose you assume that the omega here is a Hodge class, so it's first Chern class of L. Can you describe what this is? It's a priori, of course, an extended real number. Sometimes it's negative infinity. So whatever description you give of this, it has to necessarily allow for the possibility that this, again, this expression here could be negative infinity. So sometimes it is bounded from below, sometimes it's not. So that's a good question to keep in mind for my talk. This is the question that eventually I asked myself. So note that even if you get that the infimum is bounded from below, as many of you know very well, it doesn't necessarily mean that omega has a critical point. So a lower bound on the Mabuchi energy is necessary for the existence of a constant scalar curvature metric, but it's not enough. What you need is properness. And so let's recall what that is. So this is the Aubin J function. I won't give a definition. Again, it's familiar to many of you. And Tian introduced this important idea in 1997 in his Invenciones paper. So the Mabuchi energy is proper if and only if there's a positive constant delta and a non-negative constant c. This c actually depends on delta here, but I'll suppress it from the notation now, such that for all phi and beautiful h, the Mabuchi energy is bigger than or equal to this positive constant times the J functional minus c. So this is the crucial thing for the existence of Keeler-Einstein metrics, and as we'll see in a moment, metrics of constant scalar curvature. You need the Mabuchi energy to be proper. There's an extension of this, which I won't talk about. It's an extension I don't understand very well, and that's properness in the presence of automorphisms. But my talk today is really concerned with the case when the polarized manifold X is XL comma L, X comma L, it's automorphism free. So the reduced automorphism group is finite. So so the main theorem about this, about properness, appears here. So this is due to Tian in 97 in the Fano case, and Shusheng Chen and Jinguri Cheng, published in 2 papers in JAMS in 2021. And what they show is that if we assume the automorphism group is finite, then there's a constant scalar curvature metric omega phi in the class of omega, if and only if the Mabuchi energy is proper. And I think Rui, in his talk, mentioned this yesterday, that there's now a very clean understanding of the existence of a constant scalar curvature metric in a Hodge class. Let's say if we assume that the automorphism group is finite, and this is a generalization of what Tian had shown in 1997 for a Fano manifold. This is again quite a challenging result, and one of the theorems that I'll talk about today really depends heavily on this theorem here. So now our second question then is how to detect or characterize when the Mabuchi energy is proper on beautiful H with respect to some given positive delta. I think in general this is going to be quite challenging to deal with if you're not in the anti-canonical class. Somehow knowing or trying to find this delta. Right now that's a mystery. That's a mystery to me. So another way to put this question, this is an analog, obviously, of question 1, is can you describe this? Let's suppose omega, again, you can ask this question for any compact Keeler manifold, but I want to ask the question when omega is first Chern class of L, or in the first Chern class of L. So here's another question for you. What is the infimum of this? Of course, just like with the Caniggia map, this could be, and often is, certainly if delta is too big, this will be negative infinity. And it could possibly be negative infinity, and oftentimes it will be, again, if delta is too large. So here are my main results. And so to answer question 1, is that the polarized manifold is, of course, a large part of my talk consists in explaining what the words mean, is asymptotically semi-stable if and only if the Caniggia map is uniformly bounded from below. And the second result is that XL is asymptotically stable. I probably won't discuss B very much. The ideas in A are very much like the ideas in B, but there are slightly more technicalities here. I refer you to my 2021 preprint for details on strict stability. But the connection, at least with this positive integer m here, which is in the definition of asymptotic stability of a polarized manifold, is this positive integer m is connected to delta in this way. Delta is 1 over m. However, I think, and because usually when I give talks on this, I can only really discuss the first theorem. And again, the ideas in theorem A and theorem B are almost identical, slightly more technicalities here. So in my talk, I'll focus on A instead, just the uniform characterizing the infimum of the K-energy map in terms of algebraic geometry, which you can do quite explicitly. So since L is ample, we bring in the algebraic geometry into the answer by using the Kodaira embeddings. So you just pick a unitary basis, S0 through Sn sub k, of holomorphic sections of L to the k for some giant k. And then you take X and you stick it inside of your projective space in the usual way. And then let SL n sub k plus 1c be, well, it's not quite the automorphism group of this projective space. That's PGL, but for my purpose, it doesn't really matter which sort of group you want to consider with respect to your stability. You can use GL, PGL, SL, or PSL, and they're all the same. And the reason for this is simply because the Mabuchi energy is translation invariant. That's why it doesn't matter if I scale something in SL by a non-zero constant. So you take X, you fix some large K, you get yourself into this projective space, and then you pick a group element here, and you could attach to that group element a potential inside a beautiful H. And this is idea of a well-known idea of Yao and Tian, and also George Kemp. What's interesting is that George Kemp did this for an abelian variety. He could have done this for any projective variety, but he did this for an abelian variety, these Bergman metrics. And so the potential is given explicitly by this expression here, and where sigma dot the section is just you take the linear combination of the basis with respect to the group elements. And so the idea is that for each k, you can put SL n plus 1, n sub k plus 1, inside of beautiful H with this correspondence here. And the image of this map, people call it BK, are called the Bergman metrics of level K. So what we're going to do eventually is, instead of studying the K-energy map on beautiful H, we're going to take the K-energy map and restrict it to the image of this group in here. We're going to restrict it to the Bergman metrics, and then let K become very large. Again, this is a strategy that is not unknown to any of you. This was introduced in Tian's thesis in 1990, but he had in mind the Calabi functional and not the Mabuchi functional. But the reason for singling out for attention these BKs is this, again, well-known result that if you take the closure of this, Tian proved this in 1990 in his dissertation in the C2 topology, but it's known that this is true in the smooth topology. And this was first done by Weidong Ron, and then later by Steve Zeldich using the asymptotic expansion of the Bergman kernel on the diagonal. Again, well known to all of you. So as I mentioned, the motivation for doing this, at least the early motivation, Tian proposed this strategy, and he wanted to relate the properness of the Calabi functional restricted to the Bergman metrics to the stability of X in the Chow variety of degree D dimension and algebraic cycles in Pn. So early on, he just suggested as a kind of idea to follow that if you try to somehow minimize or get a critical point for the Calabi functional on each BK, and what he was imagining is that perhaps the existence of a critical point on this restricted smaller space of inside of beautiful H might be connected to the stability of X, the stability of the Chow point of X. And this is actually almost right. But what we will do, there are two things. I'm going to replace the Calabi functional with the Mabuchi energy, as you can see. And what happens is that it's not only the Chow form that comes in, the Chow point of X that enters, but another polynomial enters. Roughly speaking, the Chow form is the leading coefficient of a kind of polynomial. And this corresponds to the degree of X. But there's a subdominant coefficient, which is, well, it is ancient. The object that'll come up, it'll come up in a few slides. I called it the hyperdiscriminant. trying to follow terminology of Gelfand, Kapranov, Zelevinsky, and also Arthur Cayley. Oh, by the way, even though this gadget that Tian was contemplating, the Chow point, has the name Chow attached to it, he is not responsible for the introduction of this. This is Arthur Cayley, and all the polynomials that are going to be coming up in a few slides were introduced by him in the middle of the 19th century, to around 1848. I can remember the date because that's the date that Wisconsin officially became a state. So now let me talk about K-stability and the generalized Fataki invariant. So with the question in mind about how to detect if the Kanji map is, say, bounded below or proper, and the rough strategy is to try to ascertain boundedness or boundedness below or properness here, and then use the density theorem to transfer what you can understand, if you can understand anything at all, the boundedness or properness here to the boundedness or properness here. This is certainly what Tian had in mind already over 30 years ago. So to get started with this, and this is more or less historically what people did, you don't look at this. This is still somehow was considered to be too big. It's smaller than H, but it's way bigger, of course, than a one-parameter subgroup in here. So let's look at that. So let this be a one-parameter subgroup. So just a diagonal matrix inside of here looks like t to the a0, ... t to the an. All the exponents are integers. If we're in here, those integers have to sum to 0 to keep the determinant equal to 1. Then the limit cycle of x under lambda is defined to be, the Mumford's notation is this, like x to the lambda 0. And what you do is you move this around, lambda t inside of Pn, and then you take a limit as t goes to 0, and this is going to break up, and it'll become a projective subscheme of Pn. What you actually do officially to get this limit is you pick some m that only depends on the Hilbert polynomial of x. This comes from, I guess, results of Grothendieck or Gutzmann, and you look at the mth Hilbert point of x, and then you degenerate that in the Grassmannian, and it'll have a limit, and then to that limit you attach a projective subscheme of Pn, and that's what this is. And this doesn't depend on the m that you pick. So that's really what this object is here. So attached to that degeneration, we have this limit cycle, and also we have the corresponding Bergman potential, but now this is like a one-parameter family of potentials. And what I'm interested in right now, and as many people have been historically, you're interested in the behavior of the Kanji map as t goes to 0 along this potential. In other words, you're interested in this. This will appear, the reason for taking this logarithmic derivative, we'll see later, but this is what people contemplated in the beginning. So historically, and I'll just follow the historical path. So historical, what I mean is that one's level of understanding of this limit. So it can be understood in, now we understand what happens for an arbitrary lambda, but that's not how it started. So the first case, let me just put it this way. I put historical in quotes because it's not literally what was considered, but how can I put that? But I think it's fair to say it this way. So in 1985, Fataki and Mabuchi considered the case where the limit cycle is x. What this says is that lambda t, here, this, actually preserves x. So this is an automorphism of x, in which case x0 is just equal to x itself. So what they found is that if lambda t actually preserves x, and they did this in the case when L is equal to negative kx, so I've taken some large power of negative kx and I put it inside a projective space. What they found is that the limit of this is equal to, which will not surprise anyone, the classical Fataki invariant of x relative to this holomorphic vector field v lambda, and h omega is the Ricci potential. So this holomorphic vector field here is just the time one derivative of this one parameter subgroup. And this is going to be a vector field on x itself, since x is assumed to be preserved by lambda t. So you see that if this is an automorphism, you get the limit, the left-hand side is just the Fataki invariant. And this was actually really a theorem of Mabuchi, but I'm just going to put this to, I'm just going to say it this way, that Fataki and Mabuchi did this in 1985. So the next step was, well, if this was the first assumption that lambda t preserved x, then the next step is to contemplate, well, this case, that lambda t does not preserve x. It moves x to some other subvariety, projectively equivalent to x for t not equal to 0. And then you take the limit cycle, and then now you really have to use this Grothendieck business to get the limit. So you have two varieties now which are different. They use this. They were motivated to do this because in general, X won't have any holomorphic vector fields at all. They're still interested in the Fano case here, where L is negative kx, or some power of that. But they want to consider cases when X doesn't have an automorphism, unlike what Fataki and Mabuchi were thinking in 1985. So they jump the complex structure of X to get this new X. And then you could ask somehow the same question: how does the Canigg map behave under this limit, the logarithmic derivative of the Mabuchian, restricted to this potential? But now I don't assume that the limit cycle is equal to X. It's been moved. And what Ding and Tian show is that if you assume, I'll just say it this way, that this is sufficiently smooth, I think it was Q Fano. In other words, lambda is a special degeneration of X. Then what they showed is you get an answer which looks almost identical to the answer found by Bandhu and Mabuchi. So here on the right-hand side, this is a holomorphic vector field on X. But here on the right-hand side, V lambda is a holomorphic vector field now on the limit cycle. It's really a holomorphic vector field viewed on the regular part of the limit cycle. And H is a Ricci potential, also defined in the regular part. And the first section of their invention, of this 1992 paper, they have to spend some time showing that this potential exists and that its first derivative is integrable over the regular part. After they define this is what they call the right-hand side, they call the generalized Fataki invariant. Then they show that the limit of the Canigg map is given by the generalized Fataki invariant. So if X is preserved by lambda, then their results, of course, recover the results of Fataki and Mabuchi from 1985. Okay. So based on this result, this theorem, that the limit of the logarithmic derivative of the Mabuchian restricted to this potential is given by this integral, which is really basically the classical Fataki invariant X, but of the limit cycle. What they do is they make this definition of the generalized Fataki invariant attached to an algebraic one-parameter subgroup, or in Donaldson's language, a test configuration, with at worst normal. Well, here with that worst normal limit cycle, it means that this is the singularities of this were assumed not to be too bad. Obviously, it can't be because you need to integrate over this, and you need H to exist and so forth. But they define the generalized Fataki invariant, F lambda, to be this right-hand side here. And the main point here was that if you knew that X had a Kähler-Einstein metric, or a metric of constant scalar curvature more generally, it forces a sign on the generalized Fataki invariant. So if you're KE, then this has to be bounded. And then, well, it's not, we'll see this more precisely later, but what happens is that this left-hand side needs to be less than or equal to 0. The suggestion here is that the Mabuchian, because you're taking the log derivative, looks like a number, this number, times log t plus a bounded term. And so this coefficient in front of log needs to be less than or equal to 0 in order that the Mabuchi energy be bounded from below as t goes to 0. If it were positive, it would blow up, and there's no canonical metric. So again, the demand that the Mabuchi energy be bounded forces a sign on the Fataki invariant, namely that it has to be less than or equal to 0. So it turns out that we'll see later that this is not only a arbitrary real number, but it's in fact a rational number. And it's worth repeating that in order to define this generalized Fataki invariant, you need the limit. You need two things. You need two things come up. The limit cycle needs to be smooth. In general, it'll only be like a very bad subscheme of Pn. For example, what it'll look like in general, this limit cycle x to the lambda 0. Let's say x has dimension little n, and it has degree d in Pn. And you pick your lambda generically. And then you look at this limit cycle. Let's go back. You look at this. What will this be? Again, x has dimension little n inside of big Pn. It has degree d. This object is going to be d times a linear subspace as the same dimension of x, as x. So on the one hand, it's simple. It just will turn into a projective space. It'll turn into a little n-dimensional flat inside of this. However, it'll have multiplicity d at every single point. So quite non-reduced, quite bad in general, that limit cycle. Okay. So in 1997, so Tian introduced the idea of K semistability explicitly based on his 1992 work with Ding. And what he does, he defines K semistability in the way that we more or less know it now. You have to impose a sign on the generalized Fataki invariant for all special degenerations lambda for arbitrarily large embeddings. So what he's saying is the following thing. He says, where does this definition come from? You figure out how the Canigin map behaves along this test configuration. You figure out that it's this number. And then since you want the left-hand side to be bounded as t goes to 0, you must necessarily impose a sign on the right-hand side, namely that it be negative. And this is going to come up later in my own work, is that I'm going to do something very, very similar to this. I'm going to try to understand what the Canigin map is, express it in a way which generalizes this to a great extent, and then you impose what you need to impose on the right-hand side in order to ensure that the left-hand side is bounded. And so this is where K semistability came from. Okay, once more, so his definition of Tian's of K semistability is that you must have the generalized Fataki invariant less than or equal to 0 for all special degenerations lambda for arbitrarily large embeddings. Again, I want to emphasize is that f lambda is basically analytic in nature, and lambda must be a special degeneration in order for this to even be defined. So let's go back. See, there f lambda, the generalized Fataki invariant, is this integral here. So this is not completely algebraic, even though in 92, they studied this right-hand side here when x is a cubic surface in P3, and then found that this number was really closely related to Mumford's weight of the Chow point for that hypersurface. And they make these remarks at the end of their paper. So in order to address these 2 points, namely that now this Tian's generalized, the Ding-Tian generalized Fataki invariant requires a special degeneration. In other words, the limit cycle needs to be reasonable, and the fact that it's defined analytically still. So Donaldson wanted to make the generalized Fataki invariant completely algebraic, and what he does, and also he wants to remove any assumption about the virtues or the quality or the singularities of the limit cycle. He wants this to be completely arbitrary, x lambda. So if he's going to do something like that, then necessarily this f lambda can't be defined as an integral over this anymore, because the integral won't make any sense. So, and also another thing he does, he extends the whole picture from Fano to arbitrary polarized manifold. And the definition of K stability or K semistability today is more or less a variation on what Simon did in 2000 or 2002. So let's describe his version of the generalized Fataki invariant, which is now called the Donaldson Fataki invariant. So if we give ourselves x in Pn, so it's embedded in there, for example, by L to some very large power. So then you consider the mth Hilbert point of x. So I just won't define this, but I suppose it's familiar to many people. So given an algebraic one parameter subgroup of SLN plus 1C as usual, it's proved, for example, there's a proof of this in Mumford's paper, Stability of Projective Varieties, where he proves, I'll tell you what he proves, is that the weight of the C star action, these weights were defined in Rui in his talk yesterday. So the weights of the C star action on the mth Hilbert point of x, you can expand that in terms of a polynomial. I probably don't have the coefficients completely right. I think there are some factorials here. This is really the normalized leading coefficient. So in the denominator here, I should have some kind of n+1 factorial. I'm sure many people know the details of this more than me. So nonetheless, just to be slightly sloppy about this. So the weight of the action on the nth Hilbert point has a polynomial expansion. And then what you do is you look at the geometric Hilbert polynomial, that's P, and you multiply P times M. Now, these are both polynomials of the same degree in M, and then you take the ratio, and the ratio can be expanded like this. So this is, I'm pretty sure Rui might have mentioned this yesterday, is the weight of the Chow point of X. Again, that's well known to many people. And then we have this new thing that appears, and that's roughly speaking the, I don't know, like the subdominant, say, if you will, coefficient of this ratio, this F1. And what Simon does is he defines the Donaldson-Fotocky invariant to be this coefficient here. And then what he showed is that, well, first of all, I should make a comment, is that this coefficient is defined, and it doesn't matter what the limit cycle looks like. You can do this for, in the worst case scenario that we talked about earlier, where it's D times a linear subspace of the same dimension as X. So this is, it's quite insensitive to the extreme singularities that you'll encounter when you take t going to 0 in lambda t times X. So his Donaldson-Fotocky invariant is defined to be the coefficient of 1 over m. And then what he showed is that when the limit cycle is smooth, what you have is that his F1, this is probably not completely right, but there's some dimension constant here, like dimension and degree constant here, but it's positive. So F1 is basically equal to, he uses the equivariant Riemann-Roch theorem to prove this, that his F1 is equal to the old Donaldson-Fotocky, Ding Tian generalized Fotocky invariant / classical Fotocky invariant of the limit. So in other words, his thing generalizes what was discovered earlier by Fotocky, Mabuchi, and Ding and Tian. But now it is one completely algebraic. It's given by, well, not quite the weight of the Hilbert point, but this interesting ratio he takes, this coefficient, and the singularities in the limit cycle don't matter anymore. And then based on this, he makes this definition. So given a polarized manifold, then this is K semi-stable if and only if for all embeddings, this is like a paraphrase of his definition, but it's equivalent to it. And for all embeddings, K, and for all one parameter subgroups lambda of the special linear group, you have that just like Tian and Ding, the F1 has to be less than or equal to 0. That's K semi-stability, and K stability is that it's this sign, this inequality holds, and 0 if and only if this is the trivial one parameter subgroup. So in his language, the trivial test configuration. Okay, so what it looks like, and this is what I thought initially when I was many years ago when I was looking at Donaldson's paper on toric varieties, or toric surfaces, where he introduced this idea, is that my understanding was that what he did was to go back here, let's see, and show that this right-hand side, this is what I thought, that what Donaldson's work showed was that the left, if I look at the left-hand side here, that this is given by F1. That's kind of the suggestion that now you can understand the behavior of the Canigin map along any degeneration, and the right-hand side is equal to F1. And this right-hand side, it's plausible to think this, because now with this generalization, I have an interpretation of at least what this will be that doesn't require integration of some Ricci potential over the limit cycle. It's completely algebraic. But as many of you know, this is very interesting. This is what Tian and I found by looking at a hypersurface, and this is written up very precisely by Zhiqin Liu, is that that's actually not true. What's interesting is that this right-hand side is F1 only when this is, basically smooth or reduced. So there's something else that appears, and so let's take a look about at what that is. So again, that was very puzzling to me. And so here is the result of Zhiqin Liu in 2004. He takes a hypersurface, a smooth hypersurface in Pn+1 of some degree, degree D. And then he shows that for generic degeneration of SLn plus 2c, there is an explicit positive constant, epsilon of lambda, such that the left-hand side here, the limit of the logarithmic derivative of the Mabuchi energy is not equal to F1, but it's equal to F1 plus this positive contribution here. And he writes down an explicit expression for this. And so my attitude then upon understanding this was that what I should try and do is to identify the sum, to identify what F1 plus epsilon of lambda is. So not to try to, for example, now there's an expression of this in terms of the multiplicities of the limit cycle. This is explained to me a few months ago by Rui Dervan. And this is certainly possible to do. But what's very interesting is that you can somehow, we'll see this coming up. You can start again from the very beginning. You can, in some sense, get rid of this and then introduce, another F1 that we'll see what that is in a moment, that completely captures the behavior of the Canigin map along the degeneration. So what I want to do is I want to identify the sum. So I'm not interested in this epsilon lambda. I just want to start again, all over again, and try to figure out what this is, independent of the singularities of the limit cycle. And the path I'll follow is very similar to what Donaldson introduced. Okay. So now let me talk about stability of projective variety. So in this section, where this is going is I really want to completely rework Donaldson's ratio. I'm going to find a new numerator. It's going to look almost, it'll be in spirit very similar to this, and a new denominator. And I'll take the same ratio and I'll look at the coefficient of 1 over m, and then that will be my Photockian variant, say. Okay. So let me pause for a second to see if there's some, if there are any questions or comments. Okay, all right. So let's forge on. So let X be a smooth and linearly normal, has degree D. And recall that for any P you pick in X, so this X got in here by some high power of L. And so for any P in X, recall that the embedded tangent space to X at P is this n-dimensional projective linear subspace sitting inside of the Grassmannian. It's not the Zariski tangent space to X. It's a linear subspace of the blackboard bold Grassmannian means little n-dimensional linear subspaces of Pn. And this is obtained by projectivizing the tangent space to the cone over X. So the Zariski tangent space put to the cone over X inside of here, lying over P. And so if you give yourself any J in between 0 and n, I want to introduce a family of divisors inside of the Grassmannian. And this family of divisors is given in the following way. You consider Zj, the subvariety of the Grassmannian, and how Zj is defined. It's defined in this way. You take all planes inside of the Grassmannian of cap n minus j plus 1 dimensional linear subspaces of Pn, and you look at all those planes which meet the embedded tangent space to X non-transversely. So this inequality is important because it's not hard to see, but it is perhaps slightly tricky. It's just the rank plus nullity theorem from linear algebra says that the expected dimension of the intersection is the opposite of this. So this really should be this. So this inequality here should be reversed. It should be the dimension of this, of the intersection, is strictly less than n minus j. That's what you would get for generic E. So then you'd get an open subset of the Grassmannian. So here we take these non-generic E's and you get a lower dimensional subvariety in the Grassmannian. The question is, how lower dimensional is it? And it turns out it's codimension 1 inside of the Grassmannian, more or less generically for all, for j going from 0 to n. And observe that this is very interesting, is that there are exactly n plus 1 of these little j, of these hypersurfaces, of these divisors in the Grassmannian that you can introduce for a given x. So these j's, since they're codimension 1, they're cut out by homogeneous polynomials in the Plücker coordinates. But I want to make the polynomial more concrete. And this is how I look at this polynomial by exchanging coordinates on the Grassmannian with what are called Stiefel coordinates. And what you do is there's a map from these matrices. This is just J+1 by n+1 matrices. The superscript here means matrices that have maximal rank. And all you do is you take your matrix of maximal rank and send it to the projectivization of the kernel of the matrix. And that's a point in the Grassmannian here. And this is a dominant map. And then what you can do is you can take your Zj, this divisor that we attach to X inside of the Grassmannian, and you could pull it back up to the matrices and then take the Zariski closure. And now what you have is an ordinary irreducible. I say ordinary because there are no Plücker relations anymore. It's just a polynomial on J+1 by n+1 matrices, irreducible. Oh, sorry, by polynomial I mean the divisor that cuts out this Z upper J will be an irreducible polynomial on the space of matrices. So I like thinking of it here more because I just avoid the Plücker relations on the Grassmannian. So this Zj is an irreducible algebraic hypersurface of degree dj in this affine space. And the defining polynomial of the Zj, I'll call it delta j. So this is a delta j lives in here. It's a homogeneous polynomial of degree dj inside of wj, and it's necessarily SLJ+1 invariant. It's an invariant polynomial because it's coming from this Grassmannian. And so the zero set, that's div, of this polynomial is this divisor Zj. So observe that this delta j that cuts out these divisors is only given up to C star. And I should mention to you that all of these constructions here are due to Arthur Cayley. This is what I mentioned earlier, like this construction here is really due to Cayley, and this was done, again, in the middle of the 19th century for his own purpose. Okay, so now what I want to do is I want to, let's go back to the reason why we're here. I want to find a substitute for this, for the weight of the nth Hilbert point. So let's do that. That's what these deltas will do. So now for each positive integer m, I want to consider this multisection. So I take the space of holomorphic, really essentially multi-homogeneous polynomials, holomorphic sections over the product of all these projective spaces. So delta n lives in this one, delta n minus 1 lives in the other one, delta n lives in this one, so to speak. I take delta dot comma m. The dot here means variables on projectivization of wn, variables on the next one, variables on the last one. That's what the little dot means here. So it's like a multi-homogeneous polynomial of this line bundle Lm, and the section is given this way. All I'll do is take the deltas that we have defined, and I'll raise them to these binomial coefficient powers. It took me a while to realize I should do that. And the section of the line bundle is this. You just pull back from each of the factors, this line bundle Ln minus j, and you raise it to m to the n minus j plus 1, where this Ln minus j, or Lj, is just O of P Wj dj, because each of these delta j's is a section of this, right? Because the sections here are just homogeneous polynomials of degree dj on the space of matrices here, and delta j is such a polynomial. So this line bundle Lm lives over the product of these projective spaces, and delta m is a section of this line bundle. And observe that everything is linearized naturally with respect to SLn plus 1c. And so now, given a one-parameter subgroup lambda of G, my replacement for the Donaldson-Fatakian variant, for the Donaldson weight, F1, is this rational number, which I'll call F-1, and it's given by in the following way. So what I'll do, instead of taking the weight of the Hilbert point and dividing by MPM, I'll take the weight of this multisection and I'll divide by its degree. And if you take that, this is a polynomial of degree at most n plus 1. This also is a polynomial of degree at most n plus 1. And this can be expanded in powers of m, in reciprocal powers of m. And now we'll look at the coefficient, just like Simon Donaldson did, I'll look at the coefficient of 1 over m, and I'll call that F-1. And then my first result, I did this some time ago, but this polynomial is new. This understanding it this way is new. I just realized this maybe 5 months ago. So let lambda now be arbitrary. Then there's a complete asymptotic expansion of the Canigin map along the degeneration, and it looks like this. So this f-1 is defined for any degeneration whatsoever, and it controls the behavior of the energy along the degeneration for any limit cycle whatsoever. And also, you can see it's completely algebraic. So the Mabuchi energy is bounded below along the degeneration if and only if this f-1 is less than or equal to 0. Okay, so I'm kind of running out of time. Perhaps I might ask the organizers to allow me maybe 5 extra minutes. Sorry about this. So an easy calculation shows that f-1 is given by this ratio. You do the same calculation essentially that Donaldson did in his ratio. So it's the degree of delta n times the weight of delta n minus 1 minus the degree of delta n minus 1 times the weight of delta n. So that's the replacement for this, I don't know what the right language is, the A0 minus A1 times some degrees or dimension constants of Donaldson that appears in Donaldson's F1. And again, I'm interested in this f-1 because without exception, this is how the Canigin map behaves along the degeneration. All right. So the usual terminology for the delta n is Rx, and that's called the Chow form of X. And the subdominant one, delta n minus 1, is what I call the hyperdiscriminant of X. This is sort of consistent with terminology of Gelfand, Kopernow, and Zelevinsky, and also of Burns-Sternfeld. Sternfeld calls this the Hurwitz form of X in a recent, 2017 article of his. And so let me rephrase what it means for this to be less than or equal to 0 along all degenerations. That's equivalent to the following, that f-1 is less than or equal to 0 for all lambda, if and only if for all maximal tori t and g, the weight polytope, this is like a Newton polytope of this polynomial, divided by its degree of the resultant, or the X resultant, is dominated by the weight polytope of the discriminant of X divided by its degree. So what has happened is now there's something I think new that happens, because you see this is an inequality, this is a numerical inequality, as is conventional case stability. Some number is negative, but this is rather different, even though they are equivalent to one another. This is a polytope inequality. And this is reminiscent of the slope inequality for vector bundles over curves, for example. I have an example here, which I'll skip of this in the interest of time. So again, this is a convex compact lattice polytope. This is another compact convex lattice polytope. The polytopes depend on the maximal torus that you pick. You change the torus, you change the polytopes, and even where the polytopes live. The polytopes live in the realification of the character lattice of T. So this is another way to phrase, say, numerical semi-stability, is that this the polytopes sit inside of one. And I've known that some time ago. So let's skip ahead. This example is cool, but I don't have time really to talk about it. Okay, so the next thing I want to bring up, this is not so obvious, is that polytope inclusion is equivalent to my Futaki invariant being less than or equal to 0 for all lambda. One parameter subgroup is lambda in the group, but that also is equivalent to the lambdas being negative, so to speak, and the weight polytopes sitting inside of one another. That's equivalent to something that this took me some time to see. That's equivalent to this, is that if you take this pair of polynomials and you view them in the projectivization of the direct sum of two, it turns out, irreducible representations, and you take their torus orbits, you take r and delta, and then you take r and comma 0, and you take the Zariski closures of the orbits. Those are disjoint if and only if those weight polytopes sit inside of one another, if and only if the weights are negative for all algebraic all one parameter subgroups lambda of T. So now we have 3 ways of talking about whether or not the Canigin map is bounded below along the generations. f-1 is less than or equal to 0. The polytopes sit inside of one another, and this, the Zariski closures of the orbits are disjoint. So these 2 orbits, r to the degree of delta sits inside of this big representation, and it's irreducible, by the way, has highest weight lambda dot. And this other polynomial, delta to the degree of r, again, this is what I call delta n, and this is what I call delta n minus 1. I take each one and I raise it to the degree of the other one. Again, you do this strange thing because the Canigin map is translation invariant. That's not too hard to see. And Q is just the product of the degrees. And by the way, since we're here, the degree of this is equal to d times n plus 1, and the degree of delta is equal to n times n plus 1 times the degree of x minus the degree of x times the average of the scalar curvature of x. And it's interesting, you should check that this is indeed a positive integer, this difference here. So I take these two polynomials, I put them inside of the projectivization of these two representations, and I take their two orbit closures, and that's disjoint. If and only if f negative 1 is less than or equal to 0, if and only if the polytopes sit inside of one another. So the torus orbits being disjoint, that certainly will be implied by the big orbits being disjoint. By big orbit, I mean you can look at the orbits under all of PGL or PSL or GL or so on inside of the, again, the projectivization of the direct sum of E lambda and E mu. So then you look at these two orbits defined this way. I just take not T here, but I put all of G here, and I put all of G right here, and I look at these big orbits. So I introduce this definition. So X is semi-stable if and only if this pair is semi-stable. And what I mean by that is that the orbit closures of this pair are disjoint when you take the orbits under all of the projective general linear group. And both of these orbits sit inside of the projectivization of these two representations. That's where this is taking place. So the little bracket here means line through this direct sum. So here is my main theorem. This is what I want to talk to you about. So this is question 1. And question 1 at the beginning was, what is the infimum of the Canigin map? And here's what it is. It's essentially the logarithm of the minimal distance between the zeroth key closures of the orbits. So that's what the infimum is equal to. So this result, and this is I had many of the ingredients that I needed some time ago in a 2012 article, but only very recently did I learn how to measure the distance between them. I was trying to use the L2 metric, but it turns out it was a much more interesting metric called the logarithmic molar measure, and that's what I used to, that's the correct way to measure the distance between them. These also need to be scaled when you do this, because these polynomials are ambiguous up to C star, and I scaled them so that they had molar measure 1. The point is that the L2 distance and the L0 distance, the molar measure distance, are actually equivalent to one another. This is actually was first observed by Gerd Faltings in his famous paper, Diophantine Approximation on Abelian Varieties. So this is the main result. This is answers, as you'll see in a moment, theorem A, and I will just copy exactly the same kind of spirit of Ding and Tian and Donaldson. So now I know what the infimum is. This is an upgrade. You first consider this on degenerations. You figure out what it is. You get these F1s or F negative 1s and so on, or the generalized Fataki invariant of Ding and Tian. And then you just impose a sign on the right-hand side because you want to make the left-hand side finite. So now I know under what circumstances the Mabuchi energy is uniformly bounded from below. It's uniformly bounded from below if and only if the logarithm of the minimal distance between the zeroth key closures of the orbits is finite. And so this theorem follows from, this took some work to do, it follows from this proposition here, that if you pick a polarized manifold and you embed it in here for some large k, then you take the infimum of the Canigin map restricted to the Bergman metrics. See, this is an upgrade from looking at the Mabuchi energy along one parameter subgroups. Now you can actually talk about it here on the whole group, not just C stars and G, but all of G. Then the infimum of the Mabuchi energy is equal to essentially the logarithm of the, you can forget about the tangent, of the distance between the orbit closures plus a little o1. This little o1 means that it goes to 0 as k goes to infinity. And so let me end my talk with the definition of now of asymptotic semi-stability. And again, I'm following the same pattern that Ding and Tian did and that Simon did. So I just now, because I know what the right-hand side is, this is the inf. What you just say is that a polarized manifold is asymptotically semi-stable if and only if the logarithm of the minimal distance between the orbit closures is finite. Because that's what the infimum of the Canigin map is. If it's not algebraic, obviously you don't have anything like this. If X is not, if the manifold if your X here is just a compact Kähler manifold, then this does not exist in any way, as far as I know. So there's a version of this for stability, but I'm already over time. So I appreciate your attention. Thanks.
Thank Sean for the talk.